Hello and welcome everyone to this next lecture on Riemannian geometry. But before I start today's topic, there is a little remark regarding the previous lecture. So in the previous lecture, let me open it up. So as you can see, here I discussed with you two different type of connection. The first one was this Riemannian connection, right? Which I said that this is a connection which is metric compatible. It satisfies the property of metric compatibility. And then I defined another connection for you which is known as Levi-Civita connection, this one. And this satisfies the symmetricity condition and metric compatibility condition. The thing is, in modern literature, specifically the literature of Riemannian geometry, in that literature, this Levi-Civita connection is what is usually also known as Riemannian connection. So what I mean by that, that in the literature of Riemannian geometry, at most places, they do not define this kind of connection which is only metric compatible. Okay, they don't define it. Okay, this kind of connections can be defined, but you just keep in mind that in modern literature of Riemannian geometry, Riemannian connection is just another name given to the Levi-Civita connection. So in this entire series on Riemannian geometry or anywhere else in most of the standard books, wherever you are studying the Riemannian geometry, if you hear the name Levi-Civita connection or Riemannian connection, it should come to in your mind that it is a connection which satisfies two properties. First is symmetric, second is metric compatibility. So if I say Levi-Civita connection or I say Riemannian connection, you should always think of a connection which satisfies both the properties symmetricity and metric compatibility. Okay, so just forget about it. This kind of thing comes up in different geometry. I told you some authors make such a distinction that some authors give this connection a different name, the connection which is only metric compatible and not symmetric. Some authors give this different name as a Riemannian connection. But in most of the standard literature of Riemannian geometry, it is only the Levi-Civita connection which is there, which is symmetric, metric compatibility, and it is the Levi-Civita connection which is known as Riemannian connection. So in summary, Riemannian connection is a different name for Levi-Civita connection. Whenever I say either of the name, you must think of a connection which is symmetric and metric compatible. Okay, now let's start with the today's topic. Okay, so today's topic is actually covariant derivative along a curve. But before that, I will just give a simple definition of something which is related to the symmetricity. Okay, so this symmetricity is actually comes from something called torsion. So let me just define it because I have not defined it in the last lecture. Okay, so let me just define it. So what is a torsion? This torsion on a smooth manifold, you define this map. From where it is defined? This is defined on B. So this is B map. I'm giving it a notation B from chi m cross chi m to chi m. Okay, how it is defined? This is defined by B, so it operates on two vector field V and W. Let's say this is V, this is W. Okay, so how it operates? This operates like this: nabla VW minus nabla WV minus Lie bracket of V comma W. Okay, now what it geometrically means that we will see later, but let's first see some properties of it. And the main property is that first thing, the first main property is, let's first see this. Okay, so B is C infinity M bilinear. Okay, we will come to the geometric part, but first let's have a look at this thing. Okay, let's prove this. So what do we need to prove? We need to prove it is C infinity m bilinear. What is the C infinity m? C infinity m is the space of a smooth function defined over the manifold m, and it is bilinear. That means it has two slots. First slot the V, second slot is W. So in either of the slot, if I multiply by a smooth function, okay, then I should be able to take out f. Okay, I should be able to take out f. Similar thing can be done for the second slot, that is b of v comma fw. Then also I should be able to take that out. So I need to show that. We need to show this. To show. Okay. How do I show it? It's a simple thing. Let's do it. We will just use the definition of the map, how it is defined. So by definition, this is nabla fvw minus nabla wfv minus Lie bracket fvw, right? Okay, less. You know the properties of the connection. I told you the fine connection. So in the lower slot, the first one has f in the lower slot with the v. In the lower slot, you can simply take out the f, and this is nabla vw minus. Here you will have to apply the product rule, okay, because it is not linear in the upper slot. So first f will come out, right? Nabla wv minus, then what will happen? wfv, right? Okay, this is v minus. I hope you know the property of Lie bracket. What is this? This is f Lie bracket v comma w, then minus sign comes here, but I already have a minus sign, so minus minus plus and wfv. Okay, if you have forgotten this property, please look up at any book and check the properties of the Lie bracket. Okay, there is nothing difficult here. It's just a property of Lie bracket, and the proof is quite simple. Okay. Okay. Now you see these two terms cancel out, right? Okay. From the remaining terms, I can take f common. So f comes out, and this is nabla vw minus nabla wv minus Lie bracket v comma w. Okay. What is this? You know this expression? This is the expression for v comma w, right? It's a simple proof. That's how we prove it. Okay. So similarly, verify. Please verify. Okay. Do this on your own. This is a little exercise. GW, G comes out, B, VW. Okay. So this is a little exercise. Please verify. Okay. So this was the property of the bilinearity. Now let's have a look at another property, which is this. B v comma w is equals to minus b w comma v. What does it mean? It is anti-symmetric. Okay, it is anti-symmetric. So let's prove this. Quite simple. We will just use the definition. So let's have b v comma w. What is this? This is nabla vw minus nabla wv minus Lie bracket of v comma w. Now what do I need? I need b w comma v. That means first I need nabla wv minus nabla vw. Okay. So let's take the minus sign common. What this gives? This will give me nabla wb, this second term. This one This one, the first term nabla VW, this comes with minus sign now, plus Lie bracket of V comma W. Okay. Well, that's not quite the expression for BW comma V. For the BW comma V, what do I need? Minus Lie bracket of W comma V. Well, I can get that. How? Because we know that the Lie bracket is anti-symmetric. So minus nabla WV minus nabla VW minus Lie bracket of W comma V. Why? Because Lie bracket of V comma W is equals to minus Lie bracket of W comma V. Right? As simple as that. So you identify, what is this? This expression inside the brackets. This expression is nothing but VW comma V. That's it. I hope there is no difficulty up to here. What we have done, we have defined a map which eats two vector field and gives out a vector field. So it's assigning a vector field. Okay, how is it defined? It is defined using this expression. Okay, this expression that I have written down here, nabla VW minus nabla WV minus V comma W. It is C infinity and bilinear in both the slots, and it is anti-symmetric. Okay, now let's understand what does it represent. Basically, it represents symmetricity. You remember the connection that we defined? We said the symmetric connection. If you remember, let me show you. Let me show you what expression we used here. You see this expression? This expression? What is this? This difference derivative, covariant derivative, is equal to the Lie bracket. If you take the Lie bracket on the left hand side, basically the torsion is 0. Right? Basically the torsion is 0. That's what we are calling the symmetric thing. Okay? That's what we are calling the symmetric thing. So see, geometric representation. First thing, what is this? Nabla VW minus nabla WV. Okay, what is this? It is the anti-symmetrized covariant derivative. See what's going on in case of nabla VW. What you are doing? You are measuring that as you move in the direction of the vector field V, as you move along in the direction of the vector field V, how W changes. Then in case of nabla WV, you are, oh, I wrote down incorrectly. I'm sorry. So this is WV. Okay. So now in the second case, what you are measuring, as you move in the direction of W, how V is changing. First you are noticing how W changes as you move in the direction of V. Then you see how W changes as you move in the direction of V. If there is any difference in these two, okay, if the covariant derivative was completely symmetric, it was completely symmetric, then it would have been the same. This difference would have been 0. But we are taking some non-zero part. Okay, if it is anti-symmetric, if there is any difference, if there is no difference, then this will be 0. No problem. So this, what does this represent? This represents the difference. If you first look at the change in W as you move in the direction of V, and then you look at the change in V as you move along the direction of W. Whatever difference that is the anti-symmetric thing. Okay, that's what this represents. Next thing is you have Lie bracket. Now, what is the geometric interpretation of Lie bracket? What does this tell you? Basically, this tells you this. Let's say this is the direction of V, this is the direction of W. Okay. Similarly, here also you can do this. I'm sorry. Okay. So what it's saying, what Lie bracket represent? Lie bracket represent that if you move first along V, let's say you first moved in this direction, okay, you first moved in the direction of V, then you moved in the direction of W, right? Now let's say first you move, after this compare it, okay? So first you moved in this direction, then you moved in this direction, and let's say you are moving an arrow, you are moving a vector, you took a vector here, this was the vector, you first moved it along V, then you moved it along W, and you were here. Now you took this vector, you first moved it along W, then you moved it along V, okay? And let's say there was some change, okay? You compare the final position. What I am doing, I am comparing the final position, whether they coincide or there is some change. So first I moved in this direction, in the direction of V, then I moved in the direction of W, and I got here. Now first I moved in the direction of W, then I moved in the direction of V, and I got here. So this change, you see, this difference is what Lie bracket represent. Okay, that's what Lie bracket represents. Okay, so let me write it down for you. Okay, I will write it down for you. If you move, this is simple word. Okay, there is a mathematics behind it, but I'm giving you what it means. Okay, in simple word, along V, then a tiny bit along W, the Lie bracket, this Lie bracket measures how different your final position is compared to moving along W first and then V. Okay, this is the change, this change. This is what Lie bracket measures. Okay, so now this gives the geometric interpretation of the torsion. If this term nabla VW minus nabla WV was measuring the change, how the vector field W and V are changing as you are moving along the vector field V, how W is changing, as you're moving along W, how V is changing. That's what this term measures. Okay, this measures the difference in the final position of the vector. So if the connection if the connection is symmetric, if connection is symmetric, then both of these nabla VW and nabla WV and the Lie bracket, these are equal. That is, your torsion, I should have represented it by T, that's the standard notation, but since I have represented by B, so let me write it B. BV comma W is 0. The torsion is 0. Torsion is 0. So torsion geometrically represent, much more geometrically, it represents a twisting. There is some twisting. The rotating twisting is happening. If there is no twisting, torsion is 0. Okay. So B basically measures the failure of the connection to be symmetric. Okay. How much it is deviating from being symmetric. How much connection is deviating from being symmetric. Okay. That's what the torsion measure. Okay. So this was the one thing that I needed to define. Now let's start with the main topic, which is the covariant derivative along a curve. Initially, we define this global thing. This nabla xy. Okay, this was the map from chi m cross chi m to chi m. Okay, so it was defined over all manifold, but it might happen that some vector field is well defined only along a particular curve. It might not have been defined over the entire manifold. So that's why we need covariant derivative along a smooth curve. Okay, so first we need a vector field. Okay, vector field along a smooth curve. I hope you don't have any problem in defining it. It's just a vector field. Rather than on the entire manifold, it is on a curve. So it will assign tangent vector to each point of the curve only. That's what it will do, right? So if M is your smooth manifold, okay, M is your smooth manifold, and how do you define the curve? From some open interval to the manifold, okay, that's your curve. Gamma is a smooth curve. This is your smooth curve. Then a vector field along gamma is a map. What it does? It picks up a parameter t, a point t from the interval. So what will gamma do? From the interval you picked a point t corresponding to this, you will get a point on the manifold which is on the curve gamma t. At that gamma t, it will provide a tangent vector. So it associates t with a tangent vector at gamma t. So where is this? This is in the tangent space gamma t n, right? What's happening here? This is your manifold, right? This is your some open interval. You define a curve gamma, okay? This is your point t. Here you have the point gamma t, okay, and this is your curve x gamma t, right? That's what a vector field along a smooth curve is. So this is a smooth vector field. Okay. To each point here, it assigns a tangent vector to the corresponding point on the curve. That's what a vector field along a smooth curve gamma. Okay. Okay. Now let's come to the main. You can call it a proposition or lemma because we will prove it. Let's call it a lemma. Okay. So let this nabla be an affine connection on manifold M. Then for each curve gamma from I to M, this nabla determines a unique operator. What is this operator? This is capital D over dt. Please be careful with the notation. I'm not writing d over dt because this is the notation used for usual derivative in your undergraduate calculus. Okay, so that's why we are using a different notation. In some books they also use dt like this. Okay, but I am using this one. So d over dt, how is it defined? This is defined from chi gamma. What is this chi gamma? Chi M was the space of vector field defined over the manifold M. So what is chi gamma? It is the space of vector field defined along a smooth curve gamma. Okay, that's what it is. Simple. So this is, and this provides you another vector field. Okay, and this satisfies certain property. Satisfying, what does it satisfy? First, linearity over R. Linearity over R. Okay, what is this? You know the linearity, d over dt AV plus BW, then A comes out dV over dt, B comes out dW over dt, and A and B are coming from R. Okay, this is the linearity over R. Second is the product rule. What is the product rule? Product rule is d over dt if you have FV. Now what is the f? F is the smooth function defined over M. So first you differentiate f, df over dt v. You see, I use the usual derivative. Why? Because this is just a real valued function. So I can use my undergraduate calculus derivative. Plus v is as it is. Oh, sorry. Plus f is as it is. Now I will differentiate v, the vector field. It is a vector field. So now I will use this derivative, d over dt, and f comes from c infinity n. Okay. There is another property, one more property. What is that property? That property says that if v is induced, v is induced by a vector field y. So what does this mean? It means that I have a vector field y which is defined over entire manifold. Now what I am doing, I am restricting that y to the curve. If I restrict y to the curve, what does that mean? It means vector field, I'm operating that vector field specifically on the points of the curve. That is, I'm taking this vector field y and I'm operating it on the points of the curve, that is gamma t. It will give me a vector field, right? If I will operate y exactly on the points of the curve, it will give me a vector field, but what that will be? I'm saying that vector field is v. So v is induced by this vector field y. Okay, that's what inducing means. That the y vector field was defined over the entire manifold. By restricting it to the curve, I got a vector field on the curve. Okay, okay. So if this happens, then this covariant derivative of this vector field can be calculated in a different manner. How? You simply take this covariant derivative of the vector field along gamma dot t. Okay, gamma dot t, the velocity vector field of the curve gamma. That's what I'm taking, or the tangent vector. That's what the direction is. Okay, so this is your covariant derivative along a curve gamma. Okay, you have a fine connection and it gives you a unique operator. Now we need to prove it. So to prove it, we need to do two things. What are the two things? First thing is I need to show that such an operator exists. First we need to show the existence. Second, we need to show that it is unique. Okay. I will first show the uniqueness and you will know why. Okay. So let's first show the uniqueness part. Proof. So first I will show the uniqueness part. To show the uniqueness part, I will have to suppose that there exists such an operator. So suppose there exists such operator d over dt satisfying three properties above. That's what we will do. We can show the uniqueness only when there is an operator. So we will have to suppose the existence. We will prove the existence also, but let's first suppose there exists. Okay, and it satisfies the properties given. Okay, now I have told you always we will have to find out now how can we show the uniqueness. There are all sorts of different ways. Most common way is you suppose that there is another thing. If I want to show that X is unique, satisfying certain property, I will say suppose there is Y which also satisfy this property, and somehow through some calculation, I will show that X is equals to Y. That's what I will do to show the uniqueness. But there is another way. If you have X and I can show you that this X only depends on the things which are fixed, which are already fixed, is not depending on anything which can change. If I can show that, then I can say that X is unique because X is not depending on anything which changes or comes from different place. You will understand what do I mean by that. Okay, let's first prove it. And I have told you I need to do some calculation. I need to figure out what this d over dt has. What this d over dt, what are the things on which it depends? Let's say if it depends on two things, and if those two things are fixed, it cannot change. It is unique, right? So let's do that. Now for any calculation, whatever calculation we do in the chart. So let u x1 to xn be a chart on M. Is this assumption enough? It's not enough. because we need to study the vector field along the curve. This d over dt gives us a vector field along the curve. So I need to have a chart which contains either some part of the curve or the entire curve. Okay, so such that gamma I is contained partially or completely, properly or completely, gamma I in U. Okay, then for a vector field, then for a vector field V along gamma, let's calculate for a vector field, let's calculate this thing dV over dt. What is it? So this is d over dt. Now this is a vector field. We are in a chart, so we can write it as a linear combination of chart induced basis. So Vj t del j. Okay. So this del j is nothing but this is the notation for this. Okay. Please keep in mind. Don't get confused. Okay. It's simple. So Vj are the components of your vector field V and del J are the chart induced basis. Okay. So now we know, we have assumed that this d over dt operator satisfies those three properties. So apply the product rule. Vj is the component and del J are the basis vector field. Okay. So these are simply component functions. These are smooth function, real valued function. So this will be dvj over dt, del j is as it is, plus vj is as it is, and then d over dt del j. Okay. Now what do you think, which property you will apply here? Which property you will apply? Del j is the basis vector field. Can you see? This is the property that you can apply, this one. Because here what I am saying that V is induced by a vector field Y. So you have a vector field defined over the bigger space. By restricting it, you got it on the curve. But the same in the other way, you can also say that V is a vector field that can be extended over the entire manifold. You can extend V over the entire manifold. Well, that's what you can do with the basis vector field. That's what bases do, right? So you can apply that. So by that, this is nothing but nabla del j gamma dot t, right? Okay. So this thing is as it is, del j plus vj. Now gamma dot t, you are in chart. How can you write gamma dot t in chart? How can you write? It's a tangent vector. So you can write it in terms of chart induced basis, right? What will be the component of gamma dot t? If gamma t, the vector is defined using the component x1, x2, xn, then gamma dot t will be defined in what manner? The components of gamma dot t will be x1 dot, x2 dot, x3 dot, right? So this will become x1, sorry, not x1. So this is x dot I del I. Okay, one more thing I forgot to tell you. I'm not putting summation sign here. I'm using the Einstein summation convention. Okay, Einstein summation convention. That's what I am using. So you have here what you have, this, let's say xj and yj. You have repeated same index. If an index is repeated, That means there is a sum going on over that index. So I have wrote xj yj. So there is a sum. But if I write xi yj, is there a sum? No, because neither I nor j is a repeated index. Whenever you have a repeated index, then you always assume immediately that there is a sum over it. Okay, that's it. It's a good thing just to have clean representation of the calculation. You don't have to apply all sorts of summation sign. So here also you see I have written x dot I del I. I is the repeated index, so there is a sum. Okay, and then here we had del j, right? Okay, we are simply applying the properties of the operator. Okay, now here also you know the property of this nabla. X dot I simply the component function, so they can come out. This is nabla del I del j, right? Okay, dvj dt del j vj x dot I. What is this? I have told you this many times, right? This is a vector field. There will be some coefficients ij k del k. Okay. Now you can change the dummy index. Okay. So you can simply have like this vj x dot I k ij and del k. Now have a look at this expression. This right hand side expression that we have got for dv over dt. What does this depend on? It depends on only two things. First, since your Christoffel symbols are here, it depends on the connection. Second, the components of the vector field, which is defined along a curve, that is also there. That means it depends on the curve. If you change the curve, then the problem there will be, because these components will be different. If your curve will change, if you change the connection, then your Christoffel symbols will change. But these two things are fixed. Once you have a manifold with a particular connection, you have defined a curve, only then you are doing all this. So your connection and your curve are fixed. It does not depend on anything which changes, which may give something different. The two things on which it depends, they are fixed. So of course it is unique for a given connection and a given curve on the manifold. Okay, right? So the right hand side depends only on the connection and gamma. Therefore, d over dt is unique. Okay. So call this equation star because we need it. Now let's do the existence part. Existence part is simple, it's just a lot of calculation, nothing else. Now to show the existence, what we need to do? First, we need to define this operator, this d over dt that we have. Okay, we need to define this. If we define this by something, then we need to show it indeed satisfies those properties, those three properties that we have covered in the statement. That's what we need to show. First, we need to define it. And whatever way we define, defining is not enough. After defining, we will have to also show that it satisfies whatever candidate we will take. Okay. First, we will have to take a candidate for d over dt, and then we will have to verify that it is indeed the derivative operator that we require. That is, it satisfies those three properties. So how can we define it? do we have a candidate for d over dt? Okay, like what can be the candidate for this dv over dt? It will operate on v. You know what could be the candidate. It is in front of you. That's why I showed the uniqueness first, because I figured out what it might look like when it operates on V. What it looks like when it operates on V. This is how it looks like. So you can define it by the equation star. Okay. So simply, I'm not writing it. Define this by equation star. Okay. Then please verify. This is for you. Verify the mentioned three properties. Okay. So for example, linearity है. Okay. For example, you have linearity. So what you will do? You will take v plus w here, d over dt, and then on the right hand side, what you will get? You will get this v plus w, the kth component. Okay, dt, and similarly here also. Then you apply the properties, and you need to show it equal to what? dv over dt plus dw over dt. These are just simple calculations and manipulation. Okay, so please do this. Okay, so once you have verified this, that means the candidate that we have provided is indeed the derivative operator that we need, and it shows the existence because I have given a candidate which is working. That means there exists. Okay. Okay. And why do we need it? I have told you why do we need it, such an operator. Okay, I have told you. The reason is that sometimes it might be possible that some vector field is completely tied to a particular curve. It might not be defined over the entire manifold, or it might not even possible to define it. For example, velocity vector field. Velocity vector field is tied to the tangent vectors. It gives the tangent vectors along the curve. The velocity of a curve is completely tied intrinsically to the curve. It might possible in some cases that that velocity vector field is not well defined over the entire manifold. It is well defined only along the curve. In that case, we need such an operator. Okay, this is one small thing for today. One more small thing. That small thing is parallel vector field. Parallel vector field. Okay, so let's say you have your manifold with your connection defined over it. Okay, it can be affine connection, it can be Levi-Civita connection. Please keep in mind, I'm telling you again, Levi-Civita connection and Riemannian connection are the same thing. It is a connection which is symmetric and metric compatible. Okay, these are the same thing. Okay, so here you have simply a manifold and affine connection. Okay, then a vector field, V along a curve gamma is called parallel, is called parallel if your dv over dt is 0 for all t belongs to I. Okay, what does this mean? The covariant derivative of this vector field v along this entire curve is 0. What does that mean? That means as you go along the curve, the vector field does not change. The value of the vector field does not change. Let's understand. Let's understand. Okay. Let's understand this. I am saying that dv over dt is 0. And Earlier, I calculated that what this dv over dt looks like. If this is 0, what this means? This means that dvk over dt plus there was something, let's take it on the right hand side. This is equals to minus Christoffel symbol ij k x dot I and vj, right? Okay, this is what it means. Okay, what is this? dvk over dt. What is vk? Vk are the components of the vector field. So this represent change of the components of v in the chosen coordinates. Okay, chosen coordinates. But you see, coordinates, whatever coordinates are chosen, they are attached to the basis vectors. Basis vectors. And as you move on a manifold from one point to another point, these basis vectors also changes, right? Right? But coordinates are attached to basis vectors. To basis vectors del I, and those del I themselves themselves change as you move on the manifold, right? So what does right hand side say? This right hand side. So right hand side tells you, right hand side, this tells you that change the component just enough to counteract the basis change. Okay, you are changing the component here in the chosen coordinate, but as you are moving, the base is also changing. So these two changes are made in such a way that both are equal. They counteract. Okay, so change components just enough to counteract the basis change along the curve. What will happen because of this? Let's say if you have a vector and you are moving this vector in the manifold, and if I am saying that this vector is parallel, this means that there will be no intrinsic turning of vector. The vector itself will not turn. Okay, it will simply move along the geometry of the manifold. Okay, the only movement that is happening is because of the curvature. If there is any change in the direction, is because of the curvature. For example, let's say if you have a sphere here, okay, on a sphere, and this vector is on the north pole. Okay, you have a sphere, okay, and you are on the north pole. This vector is on the north pole, and you start moving like this. Okay, you start moving like this. Now this change in direction that you are realizing, it's not because the vector is turning. The vector itself is not turning. It's simply the geometry itself is curved. The only movement, the only change in the direction that is happening is because of the curvature, is because of the geometry of the manifold. There is no intrinsic change. Okay, so parallel vector field, if the dv over dt is 0, this represents that the actual vector in space, not just its coordinates, the actual vector does not turn or stretch, okay, relative to the manifold geometry. Understood? There will not be intrinsic turning like this. If the vector is going like this, that means that is how the geometry of space is. That is how the geometry of manifold is. Only that's why it's happening. That's all. If it was flat, it will simply move like this. There will be no change. Okay? That's all. The intrinsic, what will be the intrinsic turning? Let's say I am on the sphere, the sphere is like this, and I am moving this vector and then it suddenly turned like this. Now this turning is the intrinsic turning of the vector. This is not because of the curvature or the geometry of the sphere. If it was along the geometry, it will simply go like this. Nothing else. That's what parallel means here, that the direction remains same. Okay. So let me write down that also for you. So in as a result of this, as a result of this, the actual vector in space, not just its coordinates, not just its coordinates, actual vector in space does not turn or stretch, does not turn or stretch relative, it is relative to the manifold's own geometry. Okay, you might understand it like this. Suppose if you are a bug and you are trapped on the surface of a sphere, you are trapped on it. You have no access to the outward, the ambient space. You have no access. You are completely trapped on the surface of the sphere. Now you are moving this vector on the surface. Okay, so the only you will see that it is simply following the curvature, the geometry of the sphere like this. Okay, it's simply following like this. It's simply doing this. There is no turning here. You are simply keeping, or you can say, let's say you are moving on the sphere and you are keeping your nose in front of you in this direction. You are just moving, you're moving, and you are like this. Now your nose is pointing in this direction, but that's not because you turned your nose. You didn't turn your nose. It only because the surface, the geometry of the sphere is curved in that direction. So the only change that is happening is because of the geometry of the manifold. It is not happening because the vector itself turned in some other direction. The vector itself doesn't turn. That's what parallel means. Its direction doesn't change with relative to the manifold's own geometry. Now this idea of parallel vector field tells you give rise to something called parallel transport. Okay, so that we will discuss in the next lecture. Thank you very much. I hope you understood, and please do all these are simple routine verification. Please do this. Okay, this verification, and I have told you another one also. Which one was it? I told you this one. Okay, please do both the verification, and if you have any difficulty, for example in this case especially because this will be long calculation, if you have any problem here, let me know. I will provide you the calculation, but first try it on your own. Okay, see you next time. Thank you very much.